Hello. Today we're going to work on lesson 3.2. It's called Like a Snowball Rolling Downhill. So if you remember at the end of lesson 3.1, we talked about how simple interest is not always a good thing when we're putting our money into a savings account or a CD, and that maybe something better was out there. And so that's what we're going to look at today. So if you can go ahead and get your lesson out. And we're going to start right here on page 269 at the bottom. Hopefully you've read the intro here. It says, we've already studied how an investment can grow when simple interest is calculated. The table below is borrowed from lesson 3.1, borrowed, stolen, whatever. Our first goal in this lesson is to recalculate the interest earned in the value of the account, this time calculating the next year's interest on the entire value of the account, right here, rather than just on the principal. So kind of what we were doing at the end of lesson 3.1. Okay, so compute the amount of interest earned during the second year if that amount is 5% of both the principal amount of 600 and the 30 in interest that was already earned in the first year. Find the new ending value as well. Show work, please. So second year interest is our new principal is 630 times our 5% times the 1 year, which is going to be the second year's interest. And that is going to be $31.50. We know from lesson 3.1 that we can compute the amount of interest earned in 1 year using the formula I equals PR. This is using T equals 1 in the interest formula. Use this formula with P at 630 to show that you can get the same answer you did in question 1, which we did basically use that. Okay, number 3, it says your answer to question 1 to fill in the row of the table correspondingly to after 2 years. So after 1 year, we had 630. Then repeat your calculations to fill in the remainder of the table, keeping in mind that in each case, interest should be calculated on the new amount at the beginning of the year. Okay. So after 2 years, we would have 630 plus 31.50, so 661.50. So the next one, we would have $694.58. We would have gained $33.58 because we're getting interest off of this value. So that value is, so this value is going to give us the interest, total interest earned in this year. And so the new interest earned in year 4 is by taking $694.58 and multiplying it by the 0.05. So we're getting 34.73. And depending on how rounding goes, then we should have $729.31 in our account. So if all went well, you should have found that at the end of 4 years, the account would have $9.30 more when interest is calculated on the new yearly amount than the original principal. So there we had 720, and we have 729.31. We had 31 cents because of rounding. This type of interest is called compound interest, and each time the new amount is calculated, we say that the interest has been compounded at that time. Since interest is being compounded once per year in this example, we say that it is interest compounded annually. You're probably not overly impressed by that exact the extra $9, but when we develop this and go further and further over time, it gets even better. So let's go ahead and flip the page. So it says, we're going to look on a pattern here. So you can see here, it says value after 1 year and value after, we've got 1.05, and then we've got another 1.05. So we've got 1, 2, 1.05. So there's two of them. We developed this back in unit 2.1 when we talked about compound interest. So value after 2 years times 1.05 is 600 times 1.05 squared times another 1.05 means the new one after 3 years is going to have an exponent of 3. Okay, and after 2 years, you have an exponent of 2. So you can see that the value after the different years is going to change your exponent. So the value after 4 years is going to be 600 times 1 plus 0.05 to the 4th. And after 5 years, it's going to be 1 plus 0.05 to the 5th. And so we can then make a conjecture, which means we're kind of using previous historical evidence that we could say we could go out to 100 years and it could be 100 here in the exponent. So we're going to say after t years, it could be 600 times 1 plus 0.05 to the t years. And we just developed the formula that we're going to use here in the purple area, where A is the future value, P is the principal amount you're borrowing or lending to someone else, R is the interest rate in decimal form, and T is the term of the investment in years. And notice that T is in the exponent. Okay. So number 7 says, use the formula for interest compounded annually to find the future value of the original $600 investment at 5% after 10, 20, 30, and 40 years. Then use a simple interest formula from lesson 3.1 to find the future value if the interest is simple. So I'm going to share my Desmos screen, and we're going to work on this in Desmos because Desmos makes it much easier to use. So we're going to make a table, and they said to do 10, 20, 30, and 40. And up here, instead of Y1, I'm going to give it the expression for the future value that we just said. So I'm going to say $600 parentheses 1.05 parentheses to the X1. So I want to use the inputs right here of 10, 20, 30, and 40 in my exponent. And so after 10 years, we should have 977.34, round appropriately, 1591.98 cents. After 20 years, after 30 years, we would have 2,593.17. And after 40 years, we would have $4,223.99. Now we can use the same inputs 10, 20, 30, and 40 and make another column here with the expression that was linear. And that is 600 plus 600 times 0.05 times X1. And so that validates after 10 years, there was $900 in the account. And 10 years of adding 30 plus the 600. So then after 20 years, we have 1,200. After 30 years, we have 1,500. And after 40 years, we have 1,800. Now, I'm going to show you my paper just so you all can see it. And validate what we put in from our, this was column 1 in Desmos. And this was column 2 that we calculated. And this was our X1. So question 8, they're asking us to graph the 2 different graphs, but we're going to go back to Desmos and do that there. So I'm going to go back and share my Desmos screen here. And you can see that right over here where my mouse is moving out to the left, the bottom part of our table, there's the magnifying glass, and that will show us the graph in Desmos. So you can tell that in green is the compound interest that's growing exponentially, and then in purple is the linear. So now you can see we're on page 273 and we're in the class portion. So it says, based on what we've learned so far, if you're the one getting paid interest, compound interest is much better deal than simple. But what if you plan to invest your money for less than a year? You'd end up getting a whole lot of nothing, since the interest is compounded for the first time at the end of the first year. This would provide a competitive disadvantage for a banker, as wise investors would prefer more flexibility. At some point, bankers decided that compounding interest more often would make them more attractive to potential investors and customers. So let's say the interest is being compounded 4 times a year, which is called quarterly. Going back to our investment of $600 at 5% interest, the banker would not add 5% to the account 4 times a year. This would correspond to a far higher rate than the 5% they promised. Instead, they divide the rate by 4 and pay 1.25% every 3 months. So 5% divided by 4 is the 1.25%. The first calculation after 3 months would look like this. After 6 months, write a calculation that describes the future value using the same idea from the group portion of the lesson. Hint, how many times has interest been calculated after 6 months? Okay, so it would be the 600 principal, 1 plus 0.05 over 4, and write a calculation that describes the future value using after 6 months. The same idea portion. How many times has the interest been calculated after 6 months? So 2 times, right? 2 times. So 2 says by the time the first year is up, the interest would have been calculated 4 times. So the total exponent on the parentheses is in our future value calculation will be so the total exponent on the parentheses in our future value calculation will be, which is the number of times per year that interest has been compounded times the number of years. So N and T. So it's been compounded. If interest is compounded monthly after 5 years, it would be compounded. And this was after 6 months. So it was compounded twice after 6 months, but it was only for half of a year. So this would be 2 times 1/2. So if interest is compounded monthly after 5 years, it would be compounded 12 times 5 or 60 times. If it was compounded n times per year, after t years, it would be compounded n times t times. So I just, up here should not be nt. By the time the first year is up, the interest would have been calculated 4 times. So the total exponent on the parenthesis is in our future value calculation will be 4 times 1, which is 4. Okay. Now adapt your answer from question 1 into a formula for calculating the future value of that $600 investment at 5% interest if interest is compounded n times per year for 2 years. Your answer in question 4 will surely come in handy. Remember that the interest rate needs to be divided into n equal portions. So from our question 1, here we were supposed to write the P1 plus the rate divided by n times and this is going to be to the n. So essentially we're deriving this formula here. So A is our future value, P is our principal, R is our rate, T is our time in years. Make sure that's in years. So if you have months, you have to turn that into years. And N is the number of times that interest is compounded per year. Okay, that's our new letter that we're using. So there's a good example that you should read through on page 274 that says calculate our $600 invested at 5% compounded quarterly for 10 years. Then compare the future value calculated in question 7. Of the group portion. We'll go back to 7. So $600 is our principal, 5% interest, 4 times a year because it's quarterly. And we're going to total out of 10 years, we're going to compound that 40 times. And we put this in Desmos and we get the value of $986.17. And from question 7, we said after 10 years of compounding annually was $977.34. So we made about $9 more, not quite $9 more by compounding 4 times a year. But hey, it does add up. So question number 4 on page 2, or question number 6 on page 275 says, find the future value of the $600 investment at 5% interest using interest compounded monthly, 12 times per year, and interest compounded daily. So they want us to do monthly and daily. Okay, so I'm going to rewrite my formula just because it's always good to practice writing it so I know what I'm using here. So we have $600 times 1 plus 0.05 over monthly. So that's going to be 12 and monthly there. And we're going to this is going to be for the 10 years. Okay. And so we're going to put this in Desmos. Right here. So $600 parentheses 1 plus 0.05 divided by 12 parentheses, and then this entire parentheses goes to the exponent of 12 times 10. And now you need to put that in parentheses so that they're both up in the exponent. So we would have monthly compounding would give us $9.8821. So a little bit more, about $2 more, right? Just over $2 more. And then the daily is going to be $600. Actually, we can just the cool thing is in Desmos is we can just copy that. Control C lets you copy, and then right here, Control V for Victor. Whoops. I'm going to copy that and paste. And then for daily, instead of 12, we're going to have 365. And remember, you have to change it in both places. And we end up with 989. And rounded would be 989 and 20 cents. So you still are increasing with the increasing your number of times you're compounding, except you're not increasing by much. So number 7 says, draw a conclusion about what happens to the amount of interest as the number of times compounding yearly goes up. Then, and this question really requires some thought, see if you can come up with a reason why this makes perfect sense. A true understanding of the difference between simple and compound interest will really help. So draw a general conclusion about what happens to the amount of interest as the number of times compounding yearly goes up. Okay, so the number of times we compound, the interest will increase, but it will increase by smaller amounts. And so you can see that the difference between here and here vertically is pretty big. And then here it's bigger, and then here it's bigger. And then it's going to do that. But if we do, instead of looking at that exponentially, if we look at this compounding and we graphed these different equations with the compounding, we would see that as you compound, you're dividing your fraction here by bigger and bigger numbers. But even though your exponent is getting really, really large, what you're taking to the exponent is getting smaller. So they're kind of outweighing each other a little bit. So that's why you're not growing by as much. Okay, so the next little topic we're going to talk about on page 275 down here below is called the effective interest rate. So you're going to need to know this. This is a good one to be able to compare some things. So it says, we've now seen that the number of times interest is compounded per year has an effect on how much interest is actually earned. It's not a huge effect, mind you, but at least it's worth studying. The bottom line is that when interest is compounded more than one time per year, the actual percentage earned is a bit higher than the stated interest rate. That's good if you're the lender, not so good if you're the borrower. In any case, there's a formula that can be used to measure this effect. First, the terminology. Okay, so we're going to learn about the effective rate. Okay. So the effective rate, also known as the annual yield, is a simple interest rate that would yield the same future value over 1 year as the given compound interest rate. The interest rate is sometimes known as the nominal rate. Okay, so basically what this does is it puts all of your different compounding options on what we call apples to apples comparison. So you can really compare them as equal options instead of like, well, this one compounds more times a year, but this one is a lower interest rate. And I don't know which one I'm going to actually make more money. So this is what this does, is finding the effective rate for all of your options, puts them into equal comparisons. So E is the effective rate. And you find that by taking 1 plus your rate divided by the number of times you're compounding per year to the number of times you're compounding per year as your exponent. And then you're going to subtract 1 at the end. Okay, so make sure this is in parentheses and you have the exponent of n and subtracting 1 at the end. So A says a loan has a nominal interest rate of 4%. and the interest is compounded weekly. Without doing any calculations, would you expect the effective interest rate to be higher or lower than 4%? Okay, so this is the compounded is 4%, which means if you looked at it in a simple interest form, is actually really better. Okay, without doing any calculations, would you expect the effective interest rate to be higher or lower than 4%? I would expect it to be higher because we're going to take that nominal rate and we're going to divide by n. So they're going to, I'm going to say higher because we're going to take it to the exponent, but let's just see. So, because 9 says go ahead and calculate it. So 1 plus the 0.04 divided by weekly, which is 52 weeks, to the power of 52, subtracting 1. This is the formula we're using. Let's go ahead and get that written down and let's go to Desmos. Okay. So Desmos, we have parentheses 1 plus 0.04 divided by 52, parentheses 52, and subtract 1. So our nominal and our effective rate is actually 0.0408, 4.08%. So always go over 4 decimal places rounded so that when you turn it into the percent symbolic form, you still have 2 decimal places. So notice that I went over, this was 7.9, and I rounded up to 8. So 0.0408. So then when you turn it into this, you're comparing 4% compounding is really an effective rate of 4.08. So number 10 says, find the future value after 1 year for an investment of $10,000 at 4% compounded weekly. Okay, so weekly is n equal to be 52. So A equals $10,000. 1 plus 0.04 divided by 52 to the 52 times 1. I'm using this formula right here. Okay, so I'm going to go to Desmos. And I'm just going to go up here and delete the -1, and then in front of that, times by my 10,000. So after 1 year, we would have $10,407.95. I'll take that. So 10,407.95 here at the bottom. Number 11 says, divide your answer, question 10, by 10,000. So 10,407.95 divided by 10,000. Okay, I'm going to take that value and divide by 10,000. Interesting. We get 1.0408. And if I notice this part right here, right, is my effective rate. So this right here is my multiplier. By taking our current value dividing by our first value, that's what we did when we learned about exponential growth back in unit 2, right? And we said, oh, this is our multiplier, our growth factor. So 1.0408, and when we subtract 1, we get 0.0408, which is our relative increase. if we go back to thinking of unit 2. Okay, number 12 says, comparing investments is a very important part of any financial strategy. Which savings account is a better investment? 6.2% compounded daily or 6.25% compounded semi-annually? There are different ways you could approach this, so make sure you show all work and explain how you made your decision. So I'm going to find the effective rate of each. So the effective rate, using this formula here, is 1 plus rate over n to the n minus 1. So I'm going to do that for the first one was 0.062, but I'm compounding daily, so that's 365, and then the exponent of 365. And then this one over here is going to be 1 plus 0.0625, but it's compounded semi-annually, so only 2 times a year. So it's a little bit higher interest rate, but you're compounding only 2 times a year. So let's go and share our screen here. Parentheses, 1 plus 0.062 divided by 365. Minus 1. And then, oh, this was supposed to be a divide by 365. Okay. Now here we have 1 plus 0.0625 divided by 2. Okay. So the first one, the effective rate is 0.06396. And the second one is 0.0634777. So let's go ahead, get those jotted down, and let's go ahead and go to our paper and do a little comparison here. Figure out which one is the better deal. So this was a 6.25%. I'm sorry, this was a 6.2%. This was the 6.25%. And this was compounded 365. So 6.396, 637,634. So it looks like this one with a lower interest rate, but the more compounding actually gives you a better deal. Very cool. So let's go ahead and flip the page. Okay. If you want to take the time, you can read through this, but we are going to go right to the formula for this. What if we wanted to compound every hour of every day of every second of every hour of every minute? We are going to use a new formula, and it is going to be introduced by working through this. And if you want to read through it, you can, but it's very terse, and I'm not going to make you know how to do that. What we are going to do is skip to number 14. And so a number 14, compounding continuously, is going to be A equals P E to the RT, where E is this number here that you've just kind of, if you play through this, put this in Desmos here with 50, 100, 500. Let's go ahead and do that just for fun. So we're going to go to a table. And in the table, we're going to put the inputs of 50, 100, 500, 1,000, 1,500, 2,000 and 2,500. Okay. And then we're going to put in here the parentheses one. Whoopsie. Okay, right here. It's going to be parentheses 1 plus 1 divided by the x1, and then parentheses to the x1. Okay, so you can see it's 2.6916, 2.705, 2.716, and then it gets really, really close. You can even put in 10,000 and it, or 100,000, or actually have a million there. It gets really close and then gets so close to 2.718. So that's what we're using on our paper. It's called compounding continuously, and you're taking your principal and your base now is just this number E, and we can put in the number E in Desmos or calculator, and it's got all of the decimals, so it's very accurate, and then you raise it to the rate times time. Okay, so 15, which is our lesson check, by the way, for lesson 3.2, says use the formula you wrote in question 14 to find the future value after 20 years of a $5,000 account that earns 4% interest compounding continuously. Then compare that to the future value of the same account if interest is compounded annually. So let's just write continuous. And so that's going to be PE to the RT. And we had $5,000 to invest E, and the rate is 4% for 20 years. So let's go to Desmos to check it out here. And we've got $5,000 E. And when I put in E, notice that it goes italicized because it knows that that's what we're talking about, because we're doing a calculation, and we're going to say parentheses 0.04 times 20 years. And so after 20 years, our $5,000 would now be $11,127.70. Then they want us to compare that to compounding annually, so just once a year. So A is, let's go back to my paper here. And compounding once a year is going to be P plus 1 plus R over N to the N. So those are both 1. NT. So this is the $5,000 times 1 plus, and since N is 1 in both spots, we could just say 0.04 here. And then the 1 that goes away, and this is just to the 20. So let's see what it would be with compounding just annually, they said. 1 plus 0.05 to the 20. So compounding annually is going to be, oh, because I put in 5%, it's 4%. I'm like, that does not make sense. There we go. It should be less. So $10,955.62. Okay, so I'm going to take you back to my paper so you can see what I wrote here. Okay, so this is continuous compounding, and this is what we'd earn if we compounded just annually for 20 years. So our last and final question for lesson 3.2 says, finally, let's compare interest compounded continuously to simple interest. Suppose that $50,000 is invested into two accounts. One earns 6% interest. The other earns 6% compounded continuously. Fill in the table with the future value of each account after each term, rounded to the nearest dollar. Wouldn't this be a great spot to use a spreadsheet? And so we are going to do that in Desmos. So I'm going to put my years into X1, and then I'm going to put my calculation for simple interest here, and that is going to be the $50,000 times 1 plus 0.06 times X1 years. And then our compounded continuously is going to be $50,000 E to the 0.06 times X1 in the exponent. So let's go ahead and just share this in Desmos. And we're going to put in 5, 10, and it knows 15, 20, 25, and 30. And so for in the Y1, I'm going to delete Y1 and I'm going to type 50,000 parentheses 1 plus 0.05 X1 oops. What did I do up here? That should be a 50,000. I put my thing. Okay. So simple interest after 5 years will give us 62,500, 75,000, so on and so forth. So let's go ahead and get these filled into our table. And then in the other column, we're going to type the other calculation. And then it's going to be, oops, to the exponent in parentheses, 0.06 X1 parentheses. And after 5 years, you've already made almost 5,000 more. So 67, 492 and 94 cents. And then 91, 105 and 94. And then 122, 980 and 16. Wow, a lot more money. Look at that, compounding continuously after 30 years, 320,000. So yeah, go ahead and get those copied into your table so that you've got them in. Wow, a lot more. So that concludes our lesson 3.2, and catch me back for lesson 3.3. Have a great day.